Say you want to call a friend. You don't think about their phone number. You think about them, their name. Maybe you scroll through your contacts, tap the name, and the call goes through. Simple. But here's the thing. The phone network has absolutely no idea who your friend is. It doesn't know their name, their face, their history with you. All it knows is a number, a 10-digit string of digits that maps to a specific device, on a specific carrier, at a specific location in the network. That's all it needs to route your call. So somewhere between you thinking, I want to call Sarah, and the phone network actually connecting you, something had to translate. Something took the name Sarah and figured out what number to actually dial. That translation, that entire system of giving things human-readable names and then resolving those names into something the network can actually act on. That is what this series is about. That is naming. Now, if you've been following along with the previous series on addressing, you already know that every device on a network has an address, something like an IP address, a number that identifies where a device lives in the network so that data can be routed to it. And you might be wondering, if we already have addresses, why do we need names at all? Isn't an address enough? Let me show you why it isn't. Suppose I told you that your bank's website lives at the IP address 104.18.27.231. Okay, fine. You could memorize that. Probably. Maybe. But now suppose your bank migrates to a new data center. Their servers move. The IP address changes. Now it's 172.6.7.182.14. Well, every single person who bookmarked that address, every application that hard-coded it, every link that pointed to it, all of it breaks instantly. Or think about this. What if your bank runs dozens of servers spread across the world, and the one that responds to your request depends on where you are, what time of day it is, how loaded the network is? There isn't one address. There are many. How do you write one thing in your browser that works in all of those situations? Or simpler still, 104.18.27.231. Can you tell me just from that what website that is? What it does? Whether you should trust it? Of course not. It's an opaque number. It tells you where something is in the network. It tells you absolutely nothing about what it is. And that gap, the gap between where something lives and what it means, is exactly what naming fills. So let's actually define this carefully. An address tells you where something is. It's a location, a coordinate in the network space. It's what routers use to move your packets from one place to another. Addresses are for machines. A name, on the other hand, is a human-readable, or at least human-meaningful, identifier for a resource. It doesn't tell you where something is. It tells you what something is. Names are for people, and for the software people write. Google.com is a name. It refers to a thing, Google's web service. It doesn't tell you anything about where Google's servers are, how many there are, or what IP addresses they use. All of that is hidden behind the name, and that hiding is not a bug, it's the whole point. Because it means you can type google.com today, and 10 years from now, Google can move their entire infrastructure to different servers, different data centers, different addresses, and you'll never notice. The name stays the same. Everything underneath it can change. Names give you stability in the face of change, but a name by itself is useless to the network. Your browser can't send a packet to google.com. Packets need addresses. So before any communication can happen, the name has to be translated, resolved into an address the network can actually use. This process is called name resolution, and it's one of the most fundamental and fascinating things that happens every time you use the internet. When you type google.com into your browser, a whole machinery kicks into motion. Your computer asks a resolver, essentially a helper, "Hey, what's the address for google.com?" That resolver might ask another server, which might ask another, tracing through a hierarchy of systems until someone who knows the answer is found. The answer comes back. Here's the IP address. Now your browser can do its job. This resolution system, the one that handles domain names, is called the Domain Name System, or DNS. It's one of the most important pieces of infrastructure on the internet, and most people have never heard of it. But DNS is just one example of a naming system. Naming shows up everywhere in computer networks, often in ways you wouldn't immediately recognize as naming. When you log into a website with your username, that username is a name. It refers to your account, your data, your identity in that system. Underneath, you might be represented by a user ID number, but the name is how you and the system communicate about you. When your operating system refers to a file as /home/user/documents/report.pdf, that path is a name. It identifies a specific resource. The actual data lives somewhere on a physical disk, at some physical location tracked by the file system, but the name abstracts all of that away. When a microservice in a cloud system calls another service by something like payment service, that's a name. The actual container running that service might be on any of a dozen machines. Its address shifting every time it restarts. The name is the stable anchor. Names are everywhere. The question is just how they're structured, how they're resolved, and what can go wrong. Now here's where it gets interesting, and a little humbling. Building a naming system that actually works at scale is genuinely hard. Not hard in a "this is tedious" way, but hard in a "there are deep, fundamental tensions here that you cannot simply engineer away" kind of hard. Think about what we're asking for. We want names to be human-readable, so people can understand and remember them. We want them to be unique, so there's no confusion about what a name refers to. We want them to be stable, so things don't break when the underlying infrastructure changes. We want them to be globally accessible, so anyone, anywhere in the world, can resolve the same name to the right resource. And we want all of this to work at the scale of the internet. Hundreds of millions of names, billions of lookups per day, with new names being created and old ones changing or disappearing constantly. Each one of those requirements is reasonable on its own. Put them all together, and you start seeing tensions. If names have to be globally unique, someone has to be in charge of enforcing uniqueness, which means authority, hierarchy, and bureaucracy. If names have to be globally accessible, changes to a name's resolution have to propagate everywhere, which takes time, which means for a window after any change, different parts of the world might get different answers for the same name. If a name resolves to an address, but the resource at that address has moved, the answer is stale, it's wrong. How long do you trust a cached answer before you go check again? Too short, and you're making expensive lookups constantly. Too long, and you're working with outdated information. None of these are hypothetical problems. They're the everyday reality of how naming systems actually behave, and understanding them deeply means understanding why the internet is designed the way it is, why distributed systems behave the way they do, and why certain kinds of failures are not bugs but inevitable consequences of the architecture. Addressing tells the network where to send things. Naming tells everyone what they're sending things to, and that distinction, simple as it sounds, is the thread that connects everything coming up in this series.